Welcome to Wildcat Science with Mrs. Helgo. This is Chemistry, Chapter 5, Section 3, Part 5. And today we are going to learn more about the structure of the atom and electron configurations. So except for the mass of the atom, basically everything else is because of electrons. The size of the atom, its properties, and chemical bonding. And the configuration of how many electrons and where they are, that determines the property of the atom. So it sounds kind of important. So let's write these things down, please. An electron configuration is the description of which orbitals contain electrons. So we'll dive into that a little bit more. We know each element has a unique electron configuration, and the electron configuration contains three parts of information. One is the principal quantum number, which is the energy level or the row in the periodic table. So that's row 1, 2, 3, 4, 5, 6, 7. And then it also includes the orbitals, which are s, p, d, and f. And it includes the number of electrons. So let's look at an electron configuration. This has a quantum principal number of 1, which means it's in the first row on the periodic table. It's in the s orbital, and there are 2 electrons. So there are only 2 options in the first row of the periodic table, so we see that that is helium, because helium would have 2 electrons. Just remember, electrons always go to the lowest possible energy state. So if you're looking for which it would be, it's the one that it's not going to be in anything above that, it's going to be in that lowest one. So this isn't going to be like neon, this is going to be helium. All right, what else? I would like you to make a simplified version of this. It will help you later on. So we have our periodic table like this, and then this is 1s, and then label this 2s, and this 2p, and this 3s, and 3p, 4s, 3d, then 4p, then 5s, and then 4d, and then 5p, and then 6s, jump down here, 4f, and then 5d, 6p, and 7s, jump down here, 5f, 6d, and 7p. Okay, we'll talk a little bit more about that in a minute. There's another diagram I would like you to make in your notes. This is the diagonal rule. So on your paper, do 7 lines, do 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then on the second line, move over to the right and do 2p, 3p, 4p, 5p, 6p, 7p. And then in the third line, write 3d, 4d, 5d, 6d. And then on the fourth line, please write 4f and then 5f. We call it the diagonal rule because the electrons fill in like a diagonal. So we go 1s, and then at the end of the arrow, we come back to the beginning of the next one, and we go 2s. And then we go over here, 2p, 3s. And then we come over here, 3p, 4s. And over here, 3d, 4p, 5s. And then we come back over here, 4d, 5p, 6s. And then over here, 4f, 5d, 6p, 7s. And then our last jump is 5f, 6d, 7p. And over here, that is the order that we filled them in. So the D's and the F's kind of jump around a little bit. So that's why this will be a good diagram to keep track of those squirrely F's and D's. Okay, so let's talk a little bit more about like energy levels and orbitals before we use these rules, like the diagonal rule and then the one before, where we had our periodic table and how things fill. Okay, so just putting those two together, you don't have to make this diagram, but I think it's really useful to see how it's like, it's all laid out. So things fill 1s, 2s, 2p, then the electrons go to 3s, 3p, and then 4s, and then here 3d, and then 4p, and then they go to 5s, 4d, 5p, and then the next electrons go to 6s, then 4f, and then 5d, and then 6p, and then 7s, 4f, 6d, and 7p. So we really just take these out because that's really long and it doesn't fit well on a piece of paper. But this is what the periodic table actually looks like. Okay, let's dive into those numbers and letters a little bit more. So the primary energy level or quantum number is just like the period on the periodic table. So 1s is here, 2s, 3s, 4s, 5s, 6s, and there is 7s. And electrons are always going to fill the lowest one first, and the lowest energy levels are up here at the top. So first electron, and then the second electron, third electron, so on and so forth. Okay, so these are the 1s, 1, 2, 3, 4, 5, 6, 7, and then the quantum states is kind of where we're getting into more of the orbitals. So s, so this would be 1s, 1, 2. This would be 2s, 1, 2, and now we have a 2p. So here are the states and the orbitals. So just like I said, 1s, and then 2s, 2p, 3s, 3p, and then we get into like some d's, 4s, 4p, we get a d in there, and then when we get into the 6th and 7th rows, there's an f there as well. Okay, so elements. How does this work with each element? Well, electrons fill from the lowest energy level. So if you have one electron, it's going to be in this lowest energy level, which is 1s. So we'd say that's 1s1. When we get another one, it's going to fill the next available energy level. So it would be 1s, because this is s, and that one's s2, 1s2. If we get a third one, we have to jump up an energy level. So it would be 1s2, and then 2s1, 2s. And then this one, so 1s2, 2s2, and then we go into the p's, 1, 2, 3, 4, 5. So that's not fluorine. This red box over here should be fluorine right here. 5s. Yep, and we have 5 in, not 5s, 5p. So we have 5 electrons in the p orbital. So 9 total. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons. All right, let's add some more electrons. So now this one actually is what it's showing. Neon, if we add one more, it has a full energy level. 1s2, 2s2, 2p6. What happens if we add one more electron? Well, then we have to go into the third energy level. So here, sodium has 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going into 3s. So let's practice with helium, 1s2. So the first energy level, and then s orbital, and there are 2 electrons. So 1s2. Which period it's in, which orbital it's in, and how many electrons are there. All right, we'll practice one together, and then I'm going to have you do some on your own. So silicone, well, it has 14. So we find silicone on the periodic table, and it has 14 electrons, You don't need to write all these steps, but you do need to write out the electron configuration. So it's first row, 1s2, that's 2 electrons. Next row, 2s2. Well, we're up to 2 more, so 4 electrons. And then there's the 6, 2p6. So 2 plus 2 plus 6 is 10. And we're not full yet, so we go to the third energy level. There's 2 there, so we're up to 12. And then we could fit 6 more in the 3p6, but we don't have 6 electrons. We only have 14 electrons. So there's only 2 in that last 3p. So that's what we write. Please write this down. 1s2, 2s2, 2p6, 3s2, and then 3p2. All right, are you ready? Write the electron configuration for silicon. You should be able to do that. 1s2, 2s2, 2p6, 3s2, 3p2. All right, now I've got a harder one for you, lead. So take a minute, pause the video, and do the electron configuration for lead. And you can use your periodic table and your diagonal rule to do that. Okay, let's see how you did. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, now the f's, 4f14, jump back to d, 5d10, and then end at 6p2. Did you get it all right? So there's this thing called the noble gas notation, which you're going to find useful. And to do that, you find the noble gas before that element, and you put the bracket around the atomic symbol, and then you just do the rest of the electron configuration. So you can cut out a lot of this electron configuration. Okay, let's practice that. Please pause the video and write the noble gas notation for silicon. Okay, so if we look at silicon, the noble gas before it was neon, so we put neon in brackets, and then after neon it would be 3s2 and 3p2. Okay, write the noble gas notation for lead. Pause the video and do that, please. Okay, let's see how you did. The noble gas before that is xenon. So we put xenon in parentheses, and then after that we go to the next row. So we're at 6s2, and then we jump down to 4f14, and then back up to the transition metals, 5d10, and then just 2 in, 6p2. And we will have a chance to practice that more in class. Okay, good job. See you later.